Okay, let's go ahead and get started. For the last 3 lectures, we've been talking about how to prove that problems are hard. And specifically, we're interested in sort of the P versus NP question. Under the conjecture that most people believe, which is that these 2 sets of problems are different, this implies that certain problems can't be solved in polynomial time. Right. So no running times for these problems of the form, n to the 100 or n to the 42 log n. Nothing bounded by nothing less than or equal to n to the c for your favorite number c. But this is actually a relatively weak claim. So certain problems, for example, I'll mention 3-sat, that can't be solved in polynomial time. This might still allow running times that look like this, for example, which is bigger than any polynomial, but still relatively small. Log, log, log n. You have to make n pretty huge before this is even bigger than 2. And so an algorithm that has a running time like this would still be relatively efficient, right? On the other hand, the sort of facts on the ground is that the best algorithm known for 3-sat runs in time that's exponential in n, where here n is the number of variables in the formula. Now, the sort of obvious brute force algorithm for 3-sat says, okay, there are n variables. That means I have 2 to the n possible assignments to those variables. Let me try every single one of those. And for each one of those, I have to check every clause to see whether this variable assignment satisfies those clauses. Because this is 3-sat, there are only about n cubed distinct clauses that can be made from n variables. And we can test in a preprocessing phase whether the same clause shows up more than once. Just merge. So the brute force verification here takes time, 2 to the n times n cubed, which you can actually simplify if you're willing to, bend a little bit what 2 is. So you can do better than brute force, but you still need exponential time, as far as we know. Okay. Now, if you go further, and you look at, say, the best algorithm known for circuit sat. This algorithm runs in time 2 to the n times m, where n is the number of inputs and m is the number of wires. If you want to restrict yourself to gates that have 2 inputs, you could also define, now m is the number of wires. And essentially, this is the brute force algorithm. This is for all 2 to the n possible settings for the inputs. Use depth first search to propagate those logical values to the output and see if that output is 1. All right, so this is the brute force algorithm. This algorithm has been known since people started thinking about logical circuits sometime in the late 1940s, 1950s, when people actually started building computers out of them. Shannon came up with his, information theory as a master's student. That never ceases to amaze me. So Shannon founded an entire field as a graduate student. And part of the theory that he developed led people to think about Boolean circuits, minimizing Boolean circuits, trying to decide whether Boolean circuits are equivalent, trying to decide whether Boolean circuits are trivial, which is essentially what the circuit stat problem is asking. And in particular, this study of optimizing circuits went over the wall into Russia, and there was an entire school of Russian mathematicians who studied what they called Perigord algorithms. Perigord is Russian for brute force. Right? It really, this is a technical term that the Russian school adopted to talk about algorithms that exhaustively search the set of all possible somethings, all possible inputs to a circuit, all possible structures, all possible assignments to a set of variables, just by doing standard recursive backtracking. And so these Russian mathematicians realized circuit sat, they couldn't get any further than doing the obvious thing, but already in the 1950s, before anyone had even formalized 3-sat, they were able to show that for some problems, you can do better than the obvious backtracking algorithm by exploiting some structure that shows up in the inputs, which is the case for 3-sat. I actually have a set of lecture notes that talks about non-obvious backtracking algorithms. It doesn't give this 3-sat algorithm, but it does explain, for example, how to solve 3-sat in 1.5 to the n time. This is not all that difficult. It just requires a bit of care. So people were, in the 1950s, trying to understand what the limits were for what problems require brute force search, what problems require Perigord, and what problems don't. And the conjecture, which is, I'm putting in parentheses, or sorry, I'm putting in scare quotes because it's not really a formal thing, or at least it wasn't at the time. The conjecture was some problems require this sort of worst case exhaustive enumeration of possibilities. Now it's a little vague what this actually means. Depending on where you want to draw the lines, clearly the circuit sat is a natural category, is a natural candidate for a problem that you can't solve without exhaustive brute force. But if you look at 3-sat, on the one hand, it's not doing the obvious naive brute force. It's not doing exhaustive enumeration over 2 to the n possible satisfying assignments, but it is doing an exhaustive enumeration of a much more carefully constructed exponential size search space. Right? So it's really a matter of philosophical opinion whether you want to think of that 1.308 to the n algorithm for 3-sat as a Perigord algorithm or not. But if I take the looser condition that anything of the form c to the n, anything exponential is a Perigord algorithm, then you can take this conjecture to mean some problems just require exponential time. Later in the 1960s, when people started talking in the West about Turing machines, and figuring out the formalities of what it means for a Turing machine to run in a certain amount of time, people very quickly constructed artificial problems that definitely require exponential time. Essentially by using the same kind of diagonalization argument that people used to, Turing used originally to show that the halting problem was undecidable. You essentially lay out the acceptance rules for all Turing machines that halt in n squared time, and then you diagonalize over that, and you found a language that cannot be recognized in n squared time. In fact, you can leverage this up to any function that you compute. There is a problem which takes that much time to solve. So there is an artificial problem that requires exhaustive something, exponential something. So I really need to make this a useful conjecture to say, okay, yeah, I can construct artificial problems that require exponential time, but these are problems that I constructed specifically for the purpose of requiring exponential time. And in fact, the proofs that these things exist are not even constructive. They're just pure existence proofs. Yeah?
If we assume that p is not equal to NP, are there any non-polynomial lower bounds on the time of having the solves 3-sat?
Not that I know of. So the question is, if we assume that p is not equal to NP, can we say anything stronger than, okay, then 3-sat can't run in polynomial time? Can we say 3-sat must run in exponential time? And the answer is no. We can't, as far as I know. On the other hand, there's a more modern formulation of the Perigord conjecture. I should point out that already in 1956, somebody claimed to have proven the Perigord conjecture. So the proofs that P is equal to NP or P is not equal to NP predate the definitions of P and NP by about 20 years. So the modern version of this, which was Impagliazzo, Tassi, Zane in 1999. So for once, I'm actually going to be talking about stuff that happened in the 21st century, which is why I'm actually doing this. Formulated what they call the exponential time hypothesis. And this is actually, a formalization of the Perigord conjecture that says, let's see, what's the right way to write this down? 3-sat requires 2 to the sorry, that shouldn't be a big O, that should be a big omega because I'm describing the lower bound for all epsilon greater than 0. Sorry, that should not be for all, for some. Okay. Or equivalently, you can write this as it requires c to the n time for some c greater than 1. Okay. So the exponential time hypothesis is a statement that you might be able to improve that 1.308 to 1.3, 1.2, 1.001, but there's always going to be some constant c such that you can't get below c to the n. And so people generally believe this. This implies similar exponential lower bounds for a bunch of other NP-hard problems, in particular all of the NP-hard problems that we've seen in this class, except for technical reasons, international drafts. So maximum independent set, minimum vertex cover, maximum clique, 3 color, and therefore k color for any k, Hamiltonian path, and therefore longest path Hamiltonian cycle traveling salesman. All of these problems require at least exponential time, where in all of the cases where we're talking about graphs, n here is technically the number of vertices, because ultimately those reductions transform every variable in some 3-sat formula into some constant number of vertices in the graph. And then you have edges that are thrown in that somehow correspond to the clauses. Okay. So this is a sort of strengthening of P versus the claim that P is not equal to NP. And people generally believe this. But what's interesting is there's a stronger version of this, which is, so this is called ETH. The strong exponential time hypothesis says for any epsilon at least 0, for any epsilon greater than 0, there is an integer k such that solving ksat, which is like 3-sat, but for general values of 3. So this is, I have a conjunctive normal form Boolean formula with k literals per clause. Requires at least 2 to the 1 minus epsilon n times. So, in other words, as you increase the sizes of your clauses, the exponent, the base of this exponent gets closer and closer to 2. Okay. Another way of saying this is for any c less than 2, there exists k such that ksat requires at least c to the n time. Okay. The strong ETH conjecture, as it turns out, the strong exponential time hypothesis, as it turns out, really is a strengthening of the exponential time hypothesis. It requires a bit of technical definition chasing, but Seth implies ETH. Seth. Okay. Now, not everybody believes this. Not everybody, in particular, Impagliazzo, Patasi, and Zane are on record as saying they don't believe the strong exponential time hypothesis. Nevertheless, we have no counterexamples to this. A counterexample to the strong exponential time hypothesis would, among other things, imply that this worst-case brute force algorithm for circuit sat can be improved. Now, that improvement may be very small. It may mean just knocking that 2 to the n down to 1.9999 to the n, which is why people are a little bit hesitant to accept it as an actual conjecture. But so far as we know, the strong exponential time hypothesis is true. So there's a stronger version of a stronger version of P is not equal to NP. So the way the conjectures work is Seth implies ETH, and ETH implies P is not equal to NP. Okay. Now the reason that I'm bringing up these stronger conjectures to begin with is, first of all, just to point out that there is some subtlety in exactly what P not equal to NP means. Even if you prove that these two sets are equal, being NP hard just then would mean not polynomial, but it wouldn't necessarily imply that something is exponential. And even if you could prove that certain things are exponential, there's no reason not to try to lower the base of that exponent down as close to 1 as you want. But if Seth holds, then we're basically screwed. Right? Circuit sat, it's just brute force. Brute force, brute force, brute force. It's the only thing we know how to do. Possibly saving some low order polynomial factors or something like that, but that's not really going to be that interesting. Yeah?
You said SAS is already proved?
No. This is the strong exponential time hypothesis.
Okay. So,
Right.
Yeah.
Yeah, it's not. If Seth were proved, then we'd know P is not NP, and be a very different class last month.
So how is ETH different than P is not equal to?
So P is not equal to NP says you can't solve 3-sat in polynomial time. ETH says you must spend exponential time to solve 3-sat.
What is the
And in between, you allow for the possibility of, functions that look like this. So that function is bigger than any polynomial because log n grows beyond any constant for large enough n, but it's smaller than any exponential function because it's 2 to the log n log n, which is considerably less than any constant to the n. Right. So this is what is known as a super polynomial sub-exponential function. And if I had been thinking, I would have actually found the sheet music to the song super polynomial sub-exponential function. Anyone want to guess the tune?
I have the right model of the model.
Close.
That's Mary Poppins song.
It's the Mary Poppins song. Super polynomial sub-exponential function. Super polynomial sub-exponential function. So, not quite as good as Gilbert and Sullivan, but close. Okay. That does scan with the very model. Okay. I sense an extra credit problem.
It's got weird emphasis.
Yeah, it does. But there's another interesting set of consequences that SET has, which are as close to what we know how close to as universal as this sort of unrestricted proof that certain problems require n squared time. So when we talked about dynamic programming, we looked at things like, for example, head distance. Okay, so this is a result by Piotr Indyk and his student, who I'm ashamed to have forgotten, published in 2015, that the strong exponential time hypothesis says you can't improve the running time of the standard dynamic programming algorithm for edit distance by a polynomial factor. So here I'm defining edit distance to be, I'm given two strings of length n, and I want to know the number of insertions, deletions, and replacements required to transform the first string into the second. We saw a dynamic programming algorithm dating back to Wagner and Fisher in the late 60s to solve that problem in n squared time. There are some optimizations that we can do, right? So the best algorithm for edit distance, you can actually shave off a little bit from the n squared running time using an optimization technique that's usually referred to as the four Russians technique. Although, as usual, when things are named after people, it's somewhat debatable whether all four of them were Russians. Let's say the four Soviets, but that doesn't have the same ring. Where basically you split up the n squared size dynamic programming table into little bitty chunks of size that each contain log n entries. And then you argue that there can't be very many fundamentally distinct blocks of size square root of n by square root of log n by square root of log n. So you just pre-compute them all and put them in a lookup table. And then you do your dynamic programming over the array of n squared over log n chunks, using lookups to go from one chunk to the next instead of using the recurrence directly. So you can beat n squared a little bit, but you can't beat n squared a lot. There's no, if Seth is true, there is no algorithm for edit distance that runs in time n to the 1.99. Okay. And this really is the closest that we have ever been able to come to saying, here is a problem that cannot be solved in less than quadratic time. Right? P versus NP won't give us that. Even the exponential time hypothesis won't give us that. The most the exponential time hypothesis would imply is there is, in fact, a polynomial that lower bound for edit distance. There's some constant c such that edit distance requires n to the c time. And maybe that constant's bigger than 1. But Seth actually implies, nope, quadratic is the best we could hope for. Now I'll remind you, not everybody believes Seth. And so when I say this is the closest we've ever been able to come to actually being able to prove that certain classical algorithms are optimal, that's a very, very weak claim. It's not even like, oh, it's based on some unproven assumption that we have no idea how to prove, but everybody believes. It's based on an unproven assumption that we have no idea how to prove, and not even everybody believes it. Okay. And I also say that this is the best we've been able to do at proving n squared lower bounds, despite the fact that my PhD thesis is about proving n squared lower bounds. This just completely dominates all the stuff that I did in my thesis, because I had to assume make very, very strong assumptions about what algorithms are allowed to do, whereas this statement doesn't. This is just Turing machines. Okay. So I'm not going to be able to give you a proof of this implication. What I'd like to do for the rest of the class is sort of get close to it. Instead of edit distance, I'm going to look at something very similar, which was also proved. Longest common subsequence requires n to the 2 minus epsilon time for all epsilon. Again, this is just edit distance where you're not allowed to replace. You have to either insert or delete. And in fact, I'm going to do a weighted version of this where characters have value and you're trying to find a subsequence that is not just as long as possible, but as heavy as possible. If I say every A weighs a pound, every B weighs 5 pounds, every C weighs 70 pounds, then I'd much rather have a few C's than a bunch of A's. Yeah?
Are there any particular values of epsilon between 0 and 1 for which we can prove that?
No.
So we can't prove that you can't do it in linear time.
As far as I know, I mean, there is a lower bound that says you have to read the input. So you have to spend linear time. This is, by the way, not true of all problems, but it is true here. So if you don't read all the input, then an adversary can fool you. And that's it. The largest concrete lower bound we know for any of these dynamic programming questions is you have to read the input, unless you want to make some other complexity theoretic assumption like Seth. Okay, so we're kind of out standing over the cliff on a wire without a net saying, well, here's this hypothesis. I don't even want to say conjecture. Wouldn't it be nice if it were true because it implies all these lower bounds? Okay. Yeah.
I'm I'm just wondering the n squared divided by log n, is that smaller than n to the power of 2 minus smaller than
No. So shaving a log isn't as good. What I'm claiming is it's impossible to shave off a polynomial factor.
But what
And shaving off a log factor is much less than that. So remember, log n is much less than n to the epsilon, no matter what epsilon is. Right. There are some dynamic programming problems, not these, but there are some dynamic programming problems where the best algorithm runs in something that looks like this time. This is, serious 21st century black magic, thanks to Ryan Williams, who, just to give you some idea of, Ryan was, until a month ago, an assistant professor at Stanford, and he is now an associate professor at MIT. This function here is bigger than any polylog. It's bigger than a polynomial in log n, but it is smaller than any polynomial. So this is a super polylogarithmic subpolynomial function, which unfortunately doesn't scan with either Mary Poppins or Gilbert and Sullivan. It probably can be matched up to Hamilton or something.
It's a subregular.
Subregular?
Terminology. That it scans. Terminology not breakdown.
Okay. Super polylogarithmic subregular.
Super polylogarithmic subregular function.
Okay, it scans if you're Tom York. All right. So what I'm going to do actually first is I'm going to describe a reduction to a different problem called orthogonal vectors, and then go from orthogonal vectors up to heaviest common subsequence. The orthogonal vectors lower bound is due to the same Ryan Williams in 2005. Now, I will point out some chronology here. It generally takes about 6 years to go from having a PhD, or 7 or 8 years to go from having a PhD to getting tenure, which means that he did this when he was a student. And in fact, if I have the chronology right, he did this, he figured this out as an undergraduate at Cornell. So what's the orthogonal vectors problem? So the problem is you're given n vectors, let me call them v1 through vn, and these are binary vectors with d coordinates each. And what you want to do is determine, let me just say this as a question, are there indices I and j such that the inner product of these two vectors is equal to 0. So that means the sum from I equals 1 to d of v, or sorry, I should say k, v I k times v j k is equal to 0. So I line up the vectors bit by bit, I multiply corresponding vectors, and add up the results. Or if you prefer, I and the vectors together bitwise, and then ask if the result is the 0 vector. Okay? So this seems like a relatively straightforward problem. So let's see how you would solve it. Right? So how would you solve this problem? Right, so 4i goes from 1 to n, and for j goes from, well, I'm not going to try to optimize, 1 to n. If the inner product of vi and vj is equal to 0, return true, else return false. And this algorithm runs in time dn squared. The two outer loops each require n possibilities, and computing this inner product requires a third for loop that has size d. So I claim that this is, provided that we assume the strong exponential time hypothesis, it's impossible to do significantly better than this obvious algorithm. Okay? So let me, let's suppose we have Seth. Okay, so let me, I need to make a couple of before I talk about this lower bound directly, I need to talk a little bit more about some consequences for Seth. So one of these is that C and F sat, the limit, so if I don't put a limit on the size of any clause, this means that C and F sat requires, let's say 1 minus epsilon n time for all epsilon greater than 0. That means that C and F sat is up to, something sub-exponential, really does require the brute force enumeration of all possibilities. But now there's something a little bit weird about this. Remember when I talked about K-sat, or actually, remember when I talked about 3-sat? Let's go all the way back to the beginning. You notice there was this factor n cubed in the running time of the obvious the obvious brute force algorithm. I have 2 to the n possible variable assignments, and then I have, given that I have n variables, there are most n cubed unique clauses that I can construct from them. But when I go to C and F sat, I don't have any upper bound on the number of clauses that I can construct. And so this is a little bit weird because it's now possible that the input to C and F sat is itself exponential in n. Because for every subset of the variables, I create a clause that uses exactly that subset. And now I've created this really, really long formula, which in fact makes this statement trivial because you have to read all of the input. But now I can go back to Impagliazzo, Passi, and Zane. They actually, who are the people that proved this, it says even if every variable appears in only a constant number of clauses, which means that I only have a linear number of clauses altogether. So what they showed in particular was if you take an arbitrary CNF formula, it's possible to partition it into a fairly small number of sparse CNF formulas, meaning that each variable doesn't show up very many times. And then your original formula is satisfiable if and only if at least one of these sparse formulas is satisfiable. And so as long as you can handle the case where each variable shows up only a few times, you can use that as a subroutine to solve the original CNF SAT problem in sub-exponential time. Okay. So now let me write down the theorem that Ryan proved. That Seth implies that the orthogonal vectors problem, where I have n vectors and I have dimension log n, solving this problem morally requires quadratic. Okay, now that we're getting down into the technical guts of this, I will say something that I should have said at the very beginning, and I apologize for not saying that. You will not see any of this in homework or exam. I'm showing you this because it's cool, and because I felt like at least once this semester I should show you something that is less than 50 years old, right? So I'm going to actually try to show you something that has not even really been formally published yet, by the time we get to the end. Okay, so this was the first sort of quadratic lower bound, which says you can't be significantly subquadratic even when the size of the vectors is short. And notice now with the vectors having only length log n, then the sort of obvious algorithm runs in time n squared log n. Right? And so this is a claim that yeah, okay, I'm willing to believe that you can get rid of the log. But you're not going to bring that n squared term down to n to the 1.99. Right? And so how did Ryan do this? So this is a reduction argument. I'm trying to prove that there is no algorithm that runs in subquadratic time, so I'm going to assume there is one and derive a contradiction. Yeah?
What's the upper bound on epsilon?
There is no upper bound on epsilon. It's clear that there's no algorithm to solve the orthogonal vectors problem in n to the minus 100 time. So Seth implies that there's no algorithm to solve the orthogonal vectors problem in n to the minus 100 time. So this is in fact true when epsilon is minus 102. So it's only interesting when epsilon is between 0 and 1. Because I know for other reasons I need at least linear time, because I have to read the input. Also notice that if I think actually in terms of the number of input bits, the number of the size of my input is actually n times log n, which means this running time is actually slightly subquadratic. So it's not totally, it's not really n squared. It's not even bigger than n squared. If I really count it up carefully, it's slightly subquadratic. And the claim is I can't do better than that, significantly better than that. Okay, so let's suppose for the sake of argument that this orthogonal vectors problem can be solved in time n to the c for some constant c less than 2. Right? I'm eventually going to conclude, therefore Seth is false. Okay, so now I'm going to use this algorithm as a subroutine to solve CNF set. And so I'm going to do exactly what we normally do. I'm going to use this fast algorithm for the orthogonal vectors problem. I'm going to pipe in some sort of CNF formula. I'm going to transform this into a bag of vectors. and I'm either going to return true or false. And in particular, I'm going to return true if this set of vectors contains an orthogonal pair, and I'm going to return false if it doesn't. And by analyzing this reduction carefully, I'm going to show that the resulting algorithm for CNF-SAT runs in something less than 2 to the n time. Okay? All right, so fix a conjunctive normal form formula phi with n variables and big O of n clauses. And I'll just write the number of clauses as n. Okay? So what I'm going to do is I'm going to take the set of n variables that this formula is written over, and I'm going to split them into two subsets of size n over 2. So if you like, think of half of the variables as being x1, x2, x3 up to x something, and the other half of the variables as being y1, y2, y3 up to y something. I'm just renaming. I'm not actually changing the function that the formula represents, or the semantics of anything. I'm just assigning names. So partition the n variables into two subsets of size n over 2. Now, for each of these subsets of size n over 2, there are 2 to the n over 2 possible values for just those variables. So I'm going to call a selection of values for these n over 2 variables a partial assignment. Okay? So this is going to lead to 2 times 2 to the n over 2 partial assignments. Okay, so for each subset of n over 2 variables, there are 2 of them. I'm going to consider all possible ways of setting those n over 2 variables to true and false, and leaving the other n over 2 variables as unknown. Okay, so I've got this big exponential bag of stuff, which I'm now going to write down as a big exponential pile of vectors. Okay? So, for each partial assignment, alpha, I'm going to define a vector v of alpha. So the jth bit in v of alpha is equal to 1 if and only if alpha does not satisfy the jth clause in phi. Okay, so let me give you an example here. A or B or C, and A or B bar or D bar, and B or C bar or D, and A bar or C or D bar. Okay, so say here's my formula phi. I'm going to split the variables A, B, C, and D into 2 subsets. For each of these subsets, I have 4 possible truth values for just that pair of variables. Okay, so now I'm going to write down in red the corresponding vector for one of these partial assignments. So look at this. This is partial assignment A is true, B is true. The first clause is satisfied because A is true. The second clause is satisfied. The third clause is satisfied. But the fourth clause is not satisfied. Right? This is the only literals whose values I know are false. So whether or not this clause is true depends on the assignments to variables that I don't care about yet. So the vector for this particular partial assignment is 0, 0, 0, 1. Yes, 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 I don't know yet. Okay. For, let's say, A is true, B is false, I get yes, yes, I don't know, I don't know. So 0, 0, 1, 1. If I zoom ahead to C is false and D is false, I get the first clause I don't know, the second clause is true, the third clause is true, and the fourth clause is true. And so in particular, if I choose these two partial assignments and I glue them together into a complete assignment, where I say A is true, B is false, C is false, and D is false, then that assignment satisfies this formula. Okay, A is the only thing that's true. Okay, these two clauses are taken care of, and then C is false, so this clause is satisfied, and D is false, so that clause is satisfied. And what this sets up is a correspondence between pairs of partial assignments which together satisfy the formula, and pairs of vectors that are orthogonal. Okay. So, if I have two orthogonal vectors, v of alpha and v of beta, that's going to happen if and only if if I take the union of these two partial assignments, I get an assignment that actually satisfies the entire formula, satisfies every clause. And so, as a consequence of this, if I want to decide whether this formula phi is satisfiable or not, I build this collection of vectors, and then I ask, any pair of vectors in here are orthogonal? And if I get the answer yes, that means the formula is satisfiable. And if I get the answer no, it means the formula is not satisfiable. Okay? So, how much time does that algorithm take? Okay, so I started out by saying, let's assume that I have an algorithm for the orthogonal vectors problem that runs in time n to the c, where remember now, n is the number of vectors, right? So what happens if I pass these vectors? So if I run this orthogonal vectors algorithm on this entire collection of 2 times to the n over 2 vectors, this is going to run in time, well, it's whatever the number of vectors is to the c. But remember, c is less than 2. Right? So this means this runs in time 2 to the something less than 1 to the n for some epsilon greater than 0. All right, so for example, if c is 1.5, then I get an algorithm that runs in time 2 to the 3/4 n. And in that case, epsilon is 1 over 4. Okay. But this means Seth is false. And that's the end of the proof. Yes?
When you run orthogonal vectors, what if it finds that 2 vectors are orthogonal from the same like half of the what if it found like two possible assignments for A and B?
Okay, so there's a small technical dodge which I've left out, which is that in fact I need to add 0, 1 onto the end of all of the partial assignments to come from one set, and 1, 0 to all of the partial assignments that come from the other.
Okay.
And then that neatly avoids any questions about what if I choose 2 from this side, and you know. So I've made the vectors slightly longer, but the number of bits there is still big O of log n. Yeah.
The sense that you actually prove is you don't know if that is false or true.
No, I don't. So I
You
said
don't know
assume that the orthogonal vectors problem can be solved in subquadratic time, and I concluded that Seth is false. So equivalently, if I assume that Seth is true, then I cannot solve the orthogonal vectors problem in subquadratic time.
you just prove this.
I did a proof by contrapositive. Right. If a fast algorithm exists for orthogonal vectors, then an unreasonably fast algorithm exists for CNF-SAT. And so Seth says CNF-SAT is always slow. That implies that orthogonal vectors is always slow.
But you don't know that this suppose is true or not.
No, I don't know whether the hypothesis is true or not. It's just sort of like, well, we don't know how to disprove this, right? And it's like logically, it's a much stronger claim than P is not equal to NP. But in terms of how much people have confidence in it, it's a much shakier claim. But as I said, this is the closest thing we have to an unambiguous statement that you can't solve this problem in subquadratic time. Okay? All right. So here I was actually able to walk through the entire reduction without hiding any details, despite my attempt to hide one particular detail. For the longest common subsequence problem, I'm not going to be able to walk through all of the details of the reduction. The most I'm going to be able to do is give you a sort of high-level overview and sort of wave my hands at some of the details and say, I'm omitting about 3.5 pages of grimy case analysis. If you care, go read the paper. But the chances of anybody caring are pretty slim. In particular, I have not read the grimy case analysis. Okay, so the theorem, which was again proved just less than a year ago, is that Seth implies that the longest common subsequence problem requires n to the 2 minus epsilon time for all epsilon. Okay. So as I said, what I'm actually going to show you is a reduction to something called the heaviest common subsequence problem, or the weighted longest common subsequence problem. So I'm going to imagine that my input is 2 strings, which I will call x and y in some alphabet. This is some finite alphabet that's known in advance to the algorithm, in fact. And I have a weight function that assigns some non-negative integer weight to every symbol in the alphabet. And what I want to find then is, so I can define the weight of any string just to be the sum over all I of the weight of the ith character of that string. And so what you want to find is the maximum over the weight, all weights of z, where z is a subsequence of x and a subsequence of y. Okay. So I want to compute the weight of the heaviest subsequence that's in common between x and y. Now this is not quite the longest common subsequence problem. The longest common subsequence problem, you just care about the number of symbols in the subsequence, which is equivalent to setting the weight of every symbol to be equal to 1. But it turns out you can reduce the weighted version of the problem to the unweighted version by just taking a symbol, and if it has weight 5, just replacing it with 5 copies. If you have a symbol that has weight 8, you just replace it with 8 copies. If you have a symbol that has weight 0, you just erase it. Okay, so I can reduce this heaviest common subsequence to longest common subsequence by replace every character A with weight of A copies of A. Right. Now, actually proving that this reduction works takes a bit of case analysis. It's one of these things where you have to prove first a less than or equal to, and then a greater than or equal to. That the heaviest common subsequence of the original strings is equal in weight to the length of the longest common subsequence of these expanded strings. One inequality is straightforward, the other inequality is not. But in fact, the equality is correct. Okay. All right, so I'm going to, given that there's this reduction that allows me to add small integer weights to the characters, I'm just going to reduce to the weighted problem. I'm just going to show that the weighted common subsequence, the heaviest common subsequence problem, excuse me, heaviest common subsequence, has no subquadratic time algorithm given Seth. And in fact, now I'm going to do a reduction from the orthogonal vectors problem. So I'm playing exactly the same game that we play with NP completeness. Once I've shown that some problem is hard, for the right definition of hard, I can use that as the starting point of a reduction argument to show that other things are hard. Right. So with NP completeness, I said, let's start with circuit sat, and we get 3 sat, and then free color, and then Hamiltonian cycle, international drafts. Here I'm saying, my notion of hardness is somewhat different, but I started with, CNF sat has nothing, less than 2 to the n, less than 2 to the n. That implies that orthogonal vector doesn't have an algorithm that runs in time n to the less than 2. And now I'm going to use that to prove that this heaviest common subsequence problem, again, has no algorithm with running time n to the something less than 2. So this requires me to take a set of vectors, and in fact, I'm going to consider the version where I have 2 sets of vectors, and I want to choose one from each set. And I transform one set of vectors into one string, and another set of vectors into another string, so that the heaviest common subsequence is above some threshold if and only if there's a vector in the first set and a vector in the second set that are orthogonal. Okay, so given sets, let's call them A and B of n vectors in 0, 1 to the d, where d is, because d is relatively small. I'm going to construct strings x and y. These are going to be over a particular alphabet. Just to be sane, I'm going to okay, so my alphabet has these bizarre sorts of symbols. I'm not going to tell you the weights for now. Such that the length of the weight of the heaviest common subsequence of x and y is going to be larger than some threshold w if and only if A and B contain some pair of orthogonal vectors. Okay. So I want to encode each of these sets as a string, essentially so that it's easier to line up the strings if I happen to find an orthogonal vector, a vector in one set and a vector in the other set that happen to be orthogonal. Okay. So the reduction takes a few steps. So let me start pretty simple. First thing I need to do is describe how to represent zeros and ones. The individual bits in the vectors in the sets that make up my sets A and B. And so to do this, I'm going to define two functions, alpha and beta. So alpha of 0, alpha of 1, beta of 0, beta of 1. Alpha of 0 is going to be, sorry, let me do this correctly, always in red, open angle, x, O, close angle. This is open angle 0, x, close angle. Open angle x is open angle. Okay. Now, I want you to look at these four individual strings. And I want you to notice that if I take a string from alpha and a string from beta and I try to see what they have in common, I'm going to get three symbols in common most of the time. So alpha of 0 and beta of 0 share the common subsequence less than x greater than. The longest common subsequence of length 3. Alpha of 1 and beta of 0, again, alpha of 1 is actually a subsequence of beta of 0. So again, 3. Alpha 0 and beta of 1, less than O greater is a subsequence of length 3. But if I look at alpha of 1 and beta of 1, the longest common subsequence in that case is only 2. So by computing the longest common subsequence between these strings, I can tell whether the product of the corresponding bits is equal to 1 or to 0. Okay? So theorem is that the longest common subsequence of alpha of A and beta of B is equal to 3 if A times B is equal to 0, and it's equal to 2 if A times B is equal to 1. Okay. Now, in fact, I need to use weights because I'm going to be glomming these things together, and I want to make sure that certain things line up. So I'm going to define the weight of 0 and the weight of O and the weight of x to be 2. I'm going to define the weight of left angle and the weight of right angle to be something enormous. Okay. And I'm going to call this constant d. So now if I assign those weights, again, you get the best way to line these up is to line up the angle brackets, and then I'm either going to get 2d plus 2 if the vectors multiply to 0, and 2D if the vectors don't multiply to 0. So again, with the weights, I can distinguish between 2 bits that AND together to 1 or 2 bits that AND together to 0. Okay, now I'm going to glue these coordinate gadgets together into a sequence to get vector gadgets. Okay, so again, I'm gonna call the function alpha, but let's say I have d bits a1 through ad. I'm going to write this, again, always in red, open bracket, bullet, and then alpha of a1, alpha of a2, up through alpha of ad, close bracket. And similarly, I'm going to define beta of b1 through bd as similar idea, but I'm going to put the bullet at the end. And now to make this work out, I need to define the weight of these brackets to be really big. And I'll define the weight of the bullet in a second. So the idea is that I want to set up the weights so that the heaviest common subsequence between these two strings has one value if the vectors are orthogonal and a different value if the vectors are not orthogonal. Okay. So if I wanted to write out a particular example here, so I might write out 0, 0, 1, 1, 0 versus 0, 1, 0, 1, 1. Okay, so there are two possible things that I can do to align these two strings if I'm trying to find a longest common subsequence. The first thing is the brackets are really, really heavy. So I'm always going to match the brackets on the left with the brackets on the right. Right? The question is, this bullet is also going to be really, really heavy. And so there are really two possible things I want to be able to do. One is I want to line up corresponding coordinate gadgets. And the other is I want to line up the bullets. And these are disjoint choices. I can do one or the other. If I decide to match up the bullets, then things are in the wrong order to match up the coordinates. If I decide to match up the coordinates, things are in the wrong order to match up the bullets. And the idea is that I'm going to assign the weight of matching up the bullets to be just bigger than what you would get if all of these pairwise products are 0. So it's going to be just a little, just over the threshold that you would get. I mean, you've got a tiny +2 there, which is now, going to, accumulate here. Okay, so by setting these weights correctly, I'll be able to distinguish based on the weight of the heaviest common subsequence whether these two strings represent orthogonal vectors or not. Okay, and again, because we're running out of time, I'm now frantically waving my hands. And then finally, the last set is I'm going to turn the sets into strings. And essentially the way this works is I'm going to, what symbol did I decide on? $. That's a good symbol. I'm going to throw down some $signs on one side, and I'm going to throw down a bunch of dollar signs on the other. And now these A's and B's are actually the vectors. And if I've done this, if I did this correctly, then the best possible way of lining these things up, oops. Let's see if I can do this. Best possible way of lining these things up, I have some shift where maybe I'm going to line up the gadget for A1 to B2, the gadget for A2 to B3, the gadget for A4 to B5, and so on. If it just so happens that two of these vectors are orthogonal, this alignment will have large weight. And if it happens that none of the corresponding vectors are lined up, then the alignment will have smaller weight. And the difference between big and small is a +1. It's very subtle how this works. The trick to putting all these dollar signs and setting the weights accordingly is to make sure that the best possible alignment in all cases is shift the string so that the corresponding vectors line up for some offset, which means that now the case analysis just gets considerably simplified. So if I set all this up correctly, this is the string x, this is the string y, and the heaviest common subsequence of x and y is going to have weight larger than some threshold w if and only if a and b contain orthogonal vectors. And the thing to notice here is that the lengths of these strings are only a constant factor larger than the number of bits in the input sets A and B. Right. So if the string, each vector has length log n, you're taking two strings each with n log n characters in them. And so if you could find this heaviest common subsequence thing in n to the 1.9 n time, you could plug that in and get something that solves this orthogonal vectors problem in something like n to the 1.9 log n time, which is smaller than n to the 1.91, and so it violates that. Clearly, this requires more time than I've given it. So I thank you for letting me wave my hands frantically at you for the last 10 minutes. I am going to try to write all this down into a set of notes that I can post to the course website in case people are more interested. Again, don't worry, no homework, no exams. It's just for fun. Thank you.